Let's talk about what sine and cosine have in common. The sine function and the cosine function are both periodic functions of period 2 pi. The difference between them is that the sine function starts at 0 when the angle is 0 radians, and the cosine function, the cosine is remember the x-coordinate of the point on the unit circle, and at 0 the point on the unit circle has coordinates x equals 1, y equals 0, so cosine of 0 is 1. So the graph of the sine function and the cosine function are related in that one is the graph of the other one shifted. And we could say what that shift is by looking at a horizontal shift of pi over 2 units to the right. The graph of the cosine function shifted pi over 2 units to the right coincides with the graph of the sine function. So let's say that sine of x is the same as cosine of x minus pi over 2. That is very close to the theorem that we had about complementary angles. Just instead of x minus pi over 2, the complementary angle would be pi over 2 minus x. X minus pi over 2 and pi over 2 minus x are one's the negative of the other. Since the cosine function is an even function, the values are the same. So a way of understanding this shifting is to notice that the complementary angle theorem gives this relationship between the sine and the cosine function. Well, the point is they're so much alike, we might as well look at a family of curves that share the characteristics of sine or cosine. Those are the sinusoidal graphs. What matters about them is that they're periodic and that they have a certain scale to them. We can capture facts about them by identifying parameters of the graphs, some facts about the graphs that we could measure maybe or note and use to describe the graph. Natural ones to look at are the amplitude and the period. The amplitude is like an amplifier makes the volume control. This is like the volume control of the graph. If there is a multiplier out front, a sine or cosine of an angle, then the amplitude says what the scale should be for the y-axis. So the amplitude is the y-axis scale. It gives a sense of what the largest and the smallest values of the function can be. Another interesting thing to note is how long it takes it to cycle through a set of values and do it again. Sine and cosine are periodic functions. Sinusoidal curves are periodic functions. So we'll identify that in terms of the multiplier omega. Omega times x. Remember how it works when you are multiplying the x-coordinate of a general function graph. It has the effect of stretching out the x-axis by that factor. So cosine or sine of omega times x has period not what the period would be with omega 1, which is 2 pi, the period of the sine or cosine functions, but period 2 pi divided by omega. Let's apply these formulas. So we're going to pick out facts about the function in terms of the amplitude and the period from the numbers that are given. The amplitude is the absolute value of the coefficient out front, and the period is related to the multiplier of the x-coordinate inside for sine or cosine. So here's a particular one to try, minus 2 times the sine of 2x, and we'll figure out what the amplitude period are, and then we'll figure out what the graph looks like. So compare this template, minus 2 sine 2x, as it was given to a general sinusoidal curve, a sine omega times x. And you see you could identify a as the coefficient out front, minus 2, and omega as being 2. So the amplitude, we'll take the amplitude to be the positive value. So we'll take the absolute value of that coefficient 2. So we're going to be scaling 2 units up and down from a rest position instead of 1 unit. And we'll get t to be the value from the omega parameter in the equation as given. Omega was 2, so 2 pi divided by 2 is pi. So we want to write this as a sinusoidal curve with amplitude 2, minus means it'll go down, and t for the period of pi units. So let's start with sine of x as a generic graph, and we'll change it by doing some transformations. Sine of 2x squeezes it so that instead of having a period in an interval of length 2 pi, it has a period in length pi. That means there's room for 2 periods in the interval from 0 to 2 pi. Go back. 1 period in the interval from 0 to 2 pi. Up, down, back up again, and ready to start again. That's a period of the sinusoidal curve. The period is 2 pi. When we're doing 2 times x, there's room for 2 periods. Up, down, back to start again, up, down, back to start again, in the interval from 0 to 2 pi. So the period, there's two cycles of values in this same interval, so the period is half as long. Now let's do the amplitude. Instead of sine 2x, we want it to be minus 2 sine 2x. So instead of starting at 0 and going up to 1, we're going to start at 0 and go down to minus 2. So the amplitude minus 2 shows up there. And that's what the graph of the changed graph minus 2 sine 2x would look like. Now let's go backwards. Let's find an equation for a particular graph, and I'll show you what the graph looks like. It is, hey, it's a sinusoidal curve. Big surprise this lecture. A sinusoidal curve, and you can identify characteristics of the curve, numerical values to use based on the characteristics you can see by examining the graph. In particular, what you might notice is that this graph seems to go up and down to plus or minus 4 on the y-axis. And it is laid out so that it completes a full cycle of values, down, up, ready to start again. From here now it looks the same as it looked back here. Start again after 2 units. So I would recognize the period of this graph as 2 and the amplitude as 4. So let's write down what the equation should be with period 2 and amplitude 4. Since t, the period, is 2 pi divided by omega, we know t, pi is pi, and omega is the number that goes in the equation. So 2 pi, plugging in the numbers we know, 2 for t, gives omega equals pi. The equation is going to be minus a sine omega x, since the graph starts out going down. So minus amplitude 4 minus 4 sine omega times x. We calculated omega was pi. This graph has equation y equals minus 4 sine pi times x. Another variation on how the graph could change is to consider a phase shift. This extra piece in here, a phase shift, shows up as a horizontal transformation. Now the algebra of it is that if you've got the omega related to the period already built into the equation, so omega times x, to write down the formula for a horizontal shift, we need to write it in terms of x instead of x being, it would be x plus or minus a constant. So the constant gets factored out with this extra divided by omega. So with omega bigger than 0, we've got amplitude and period, and the numbers that show up, omega and phi, as built into the equation, the phase shift is phi over omega. What that corresponds to is a horizontal shift in the graph of the function. So we'll take a basic sinusoidal curve, we'll stretch it to account for the amplitude, along the y-axis, we'll stretch it or shrink it along the x-axis to account for the period, and after we've done those things, we'll shift that graph to the left or to the right to account for the phase shift. So here is a general curve to consider. Y equals minus 3 times the sine of the quantity pi times x plus 2, and figure out what the graph looks like. So let's pull these parameters out. The general shape of it is a sine omega x minus the phase shift phi. So the a would correspond to that coefficient out front, minus 3. We'll write down omega as the multiplier of x inside, that's pi, and phi is minus 2 to make it omega x minus phi compared with the function as given, and we'll see how to account for that. So the amplitude, we're going to stretch this thing 3 units, and we'll keep track of the minus by going down when we start. The period, in terms of the relation between the period t and that multiplier of the x coordinate omega, t is 2 pi over omega, so canceling the pi's out with omega equaling pi, we get 2 for the period. And the phase shift is phi over omega, making it match the horizontal displacement from the general shifted equation. Phi was minus 2 that we identified, omega was pi that we calculated, so minus 2 over pi for the phase shift. And now let's graph this thing. There's the basic graph, sine of x. First of all, we'll incorporate the amplitude. So minus 3 sine x. Let's go back and forward. Back is over and up 1 unit for sine of x. Minus 3 times sine of x is over and down 3 units. So that's the relation that comes out from accounting for the amplitude and the fact that it's a negative coefficient. Now let's change the scale. Instead of making it of period 2 pi, we want to make it of period 2. So what that did, let me go back and forwards. Instead of going from pi to 2 pi, we're going to go from 1 to 2 to start it again. 0 to 2 pi for the unscaled graph. 0 to 2 for the scaled graph. And the last change is that phase shift. The phase shift was minus 2 over pi. So what we want to do is take this graph and move it back 2 over pi units to get x plus 2 over pi as the shifted graph. So 3 changes to the sinusoidal curve that was the base graph that gives the shape of this new function.